So if I go ahead and just take an L transpose and hit it with both sides, I get what's called the normal equation. I think everyone's already seen this, but I'm just reviewing it real quickly. But notice I have an approximation sign here still. Because just by multiplying Lm approximate equal to d by an L transpose does not necessarily mean I've gotten rid of my approximation sign. But I'll show you visually, we will. That is, the quick and dirty way to get the solution of this guy is simply multiply both sides by L transpose M equal to L transpose D. And without proof, this approximation sign turns into an equal sign, and therefore the solution is equal to L transpose L inverse L transpose D. And that's in one step, one MATLAB line of code. Instead of doing a Monte Carlo search, we'll find that. So, the question is, how did we get rid of that approximation sign? Anybody? How can we prove that? Well, there's algebraic ways of proving it, then there's a quick and dirty way of proving it. Take a derivative along the M1 direction, you get that formula. That's a 2. But in general, we can turn that into a vector, and we call that gradient of epsilon. And if there is a solution, a least squares solution, then that least squares solution exists here. And that means that that solution we're going to call star, or optimal, has this kind of behavior. So we rearrange this guy as L transpose M star equal to L transpose D, rearranging this guy into this general matrix vector notation. Notice these are components, this is the vector now. So I rearrange this into that. Equal to 0, then I rearrange them and get this normal equation. So we know that there's a point under that curve that is 0 simultaneously. If that's true, then this equation follows. And we can find that point. And it's given by this. And therefore, that point exists. This assumes that the inverse exists. You don't have any 0 eigenvalues. Therefore, that means implicitly that we got rid of the approximation sign and replace it with an equal sign. Because this is true visually. If that's true visually, there's no approximation sign here. And that's exactly the equation we have over there. That's the quick and dirty one. Okay. So we define inconsistent we've defined overdetermined when the number of equations is greater than the number of unknowns. We've also defined the least squares solution. And let me draw a picture of that. Well, I've already drawn most of it. So the least squares solution, as given by M star is equal to L transpose L inverse. D is given by, this is all in the PowerPoint. So M star is given by that. Often what we do is we don't have a starting model of M is equal to 0. It implicitly implies that. What we'll do is we'll start off with some wrong estimate. We'll call it M0. And with M0, we can determine D0 associated with it. That is, you have some trial model and it predicts a trial data. Therefore, we can multiply this by L transpose, right? We don't have to worry about the approximation sign because we know that's true in general. Let's move this back over here. Note that L transpose L is the same as L transpose L here. What's different is this has M star in it, where this is the observed. This has M0 in it, where this is the data associated with our starting model. And our starting model is right here, so that data will lead to some kind of residual. It's that high. Let's subtract these two guys. And we get L transpose L and 0 minus M star equal to L transpose D minus D held a star. Okay. Now, let's assume we have the resources to find the inverse of it. Now, with a 2 by 2 matrix, of course we have the resources. But if we're dealing with machine learning, these guys are way, way too big. Millions by millions of dimension. But let's assume we can afford to invert that. Okay. So what's the geometric meaning of that, Marco? Here's our M0, sup 0. Here's our M star. Okay, so it's a vector that's parallel to the difference vector between our guessed solution and our actual solution. Now, we can't afford to do this. Let's rearrange this so that we have what our desired solution is. And we have this. And I'm going to call this guy residual. Except this is the minus residual, minus delta. So we have a delta D. Where is this value? Delta D. rearrange this to get that. Here's our desired solution, where we're at the bottom of the hole. Here's our starting model, and here's our residual. We can't afford to do this. So if we make a diagonal dominant approximation, diagonal dominant approximation, what does that mean, Marco? This matrix is diagonally dominant.
It's like we find the auto engine value.
Pardon me?
This is find the engine value of the matrix. This is a quadratic and
Okay, so one way to define that is to take the absolute value of the sum of the off-diagonal components for any row, and that has to be much smaller than the diagonal component. Okay. And so the diagonal component is bigger or dominates its off-diagonal components. So one way to approximate that is if the diagonal components are roughly the same, then we can say that's proportional to a identity matrix times some constant. So let's make that approximation. So we replace that with identity matrix. Identity matrix times L transpose is the same thing as before. The only thing that's left over is this term we're going to call alpha, a little bit different than beta. But this is called the steepest descent formula that is used by neural networks. There are better ways to approximate this guy. You can actually take the diagonal components of L transpose out and turn them into the diagonal components of this. In that case, this would be a D.
so as long you just multiply you just sum over the
Here's the 1, 2, 1, 3, L1, M, right? The first row of this guy is
so beta is a vector, you're not a scalar.
What?
In this case, beta
Oh, beta is a scalar.
is a scalar.
Now, a better approximation would be this. 1 over L11 squared, 1 over L22 squared. And then in that case, I put a D here or something. And this is called a simple diagonal preconditioner, which is better than this, but for simplicity, I'm not going to do this. Let's just put an I there so that you don't see the I. So this is called a steepest descent formula. This guy, and its approximation to the actual inverse. This guy is the step length. And it's determined by, could be by trial and error. Just move along a contour to move it along this direction. This is the direction until you kiss a contour. I'll explain what that means in a minute. Any questions so far?
I have one.
Yeah.
Is it always possible to convert any matrix into diagonal dominant matrix?
No.
What kind of matrix cannot be converted into diagonal dominant matrix? Is there any general condition for that?
No. I mean, it's like saying, okay, you have each equation represents a solution to one equation, say for a 2x2 equation. The solution can be along this line here. A second equation could be along this line here. No, that's not going to give me to where I want to go. Well, okay, let me give you an example, a counter example. 0, 5, 5, How do you, what's the solution to that?
5, 5.
Okay, so there's many solutions to that.
Yes.
And if there's many solutions to something, you have a non-unique system of equation, meaning with zero eigenvalues. How do you convert that to something with a unique solution to non-zero eigenvalues? Okay, anyway. Okay, so I call this the gradient. Okay, I call that the gradient because all of you convinced me that you've already gone through the algebra to do something like this, right? Well, if we call this guy delta D, why do I call that delta D? Here's our observed, here's our predicted. So by definition, that's delta D. So this I call gradient. What do I mean? Well, if I'm here, the gradient points someplace. If I'm here, the gradient points other places. But I claim the gradient points uphill. And let me prove that. See, we're going back between algebra and geometry, for understanding our equations. Okay? So let's show the geometrical interpretation of a gradient. So here's our let's take epsilon of r here. So r, well, let's call this m. And let's go along this is the so I plotted the contours on the M1, M2 plane. So this is M1, or M1, and this is M1 plus DM. I'm on the same contour. And therefore, this guy must be DM. So if I were to take a line that goes from here to here, that would give me M1. A line from here to here would be the M1 plus DM, and therefore, this is the DM vector. What's the value of epsilon here? Look, man.